How's it going, guys? Matt here from Code Tech Tutorials. We're going to be looking at Dijkstra's algorithm, and today I'm just going to kind of go over it in like a lecture type form, and we're going to walk through an example. And then in a later episode, maybe some kind of bonus midweek episode or something, we're going to code it up and make an example that you might use in an actual game or something. But today we just want to get an understanding of the algorithm. Because I don't know about you, but when I read Dijkstra's From an Algorithms book, I had to reread it like 3 times, all the math stuff, and it seemed very complicated, but really it's quite a simple and somewhat beautiful little algorithm. So we're going to make it as simple as possible. The goal is really for it to just kind of stick in your head and you to be able to apply it a little bit after watching this. So that's the main goal. All right, well, let's jump into the blackboard. Dijkstra's algorithm. Dij. This is often used in, well, all over the place. Initially, of course, you might think it's used in games, but it's also, well, it is used in games, of course, for pathfinding, but it's also used for other stuff too, including like network traffic and basically any sort of traffic. Any sort of traffic that has to pick different directions and try to find the best way. They often use Dijkstra's. There are other algorithms too. I'm not saying this is the only one, but it is a very common one and it is pretty efficient. I believe it is n log n, and we might go over that more later. It is a very greedy approach, which we might talk a little bit more about later, but let's go ahead and set up an example map. So you need a map or a graph, not the map from C++, but an actual map. So we're just gonna make some nodes. All right, so I got a bit of a palette here, just these 3 colors to use. I think that should be enough. All right, so let's make a map. Let's go ahead and just define some nodes here and see what we can basically come up with here. Let's stick with letters. We'll make this node A, and maybe we'll make a B down here, a C over here, and we're gonna connect these up. A D over here, E over here, maybe an F down here. Now this setup doesn't matter a whole lot. The way it's displayed visually doesn't matter a whole lot. It's just, we gotta make some sort of example. We also need, I'm gonna use a column here. So this might be defined as like, each of these rows might be something like a node struct. So you have each of these, right? This is obviously what the node is named. The second column, I guess you would call it like an efficiency. We call it the shortest distance from the starting point. Now we are going to define the starting point as A. You don't necessarily have to do that, but you have a starting point always, right? Every time you run this algorithm. And what this algorithm does is it runs from your start and then to your finish. So you also need to know where you're going or where you want to go. Let's make some dots here for these. Dot. Usually if you build this as a function, you pass in the entire graph and then a start and a finish, and it runs it from there. We haven't drew the lines yet, clearly, but if this were some sort of map, maybe you have some objects you're not aware of, like maybe there's a canyon here or something with no bridge or a river, so there's no crossing that. Or if you do cross it, it's very expensive. And maybe if you go straight from A to D, it's a nice long straight stretch, but you know, there's a lot of scenarios, and that's where the weights come in. This last column is the previous vertex. Okay, so when you set up this algorithm, let's go ahead and just define this graph. Now I am going to do this like randomly, basically, and some other random connections here. We'll make like a G, because I want to have some varying cases basically so that you can really see it work. Okay, so now it's starting to look a little map-like. We've got some different options. All of these, we'll call them roads. These connections all have a weight or a difficulty. On a map, this might be like how many miles it is, or on a game, it might be how difficult is the grid cell. Is it quicksand? Is it water? Or is it simple terrain? You know, it's something like that. And basically we assign it a number. So let's say going straight from A to F, that this one's super difficult. So we're going to give it a 10. And we also need to add G to this little thing here. So we'll do that real quick. And we should probably put some titles. I believe the setup is actually rather important. I think partially the setup is what helps it stick in your brain a lot. Now let's say that we want to go, just for this particular example, Of course, you could pick anything. We're going to assume that the start is A, and we're going to assume the finish is E. We're attempting to get to E. Nice crayon drawing there. So the goal is to get from A to E in the cheapest way possible. And in a very simple graph, you're going to be able to just sample up these numbers and probably eyeball it and be able to tell. But what happens when it's really complicated, or when you need to do it a million times over and over, a bunch of times a frame, or it's network traffic and there's no way you can eyeball it? That's the point of this algorithm. So in this example, you're going to look at it and think, oh, that's obviously the shortest path. But the point is the algorithm, not that you can eyeball this simple example. Let's fill these out. We're going to be calling this distance, but it's not necessarily always called distance. Sometimes it's called like difficulty or something like that. But it is an edge that goes from one node to another. And we are also assuming that these can go both ways, that you can go back or forth. But for our cases, generally, we're always going to go forward here. You typically don't want to visit a node and then go back. Actually, it doesn't even allow that, as we'll see shortly. When you start, now this is a minimizing algorithm. Basically means it's going to minimize your options. It's going to take away all the bad options, and you're going to be only left with the best. And when you visit nodes, you visit the one with the smallest distance from A next, and you just keep doing that until you visited all of them. So what this ends up meaning is that you have an open set and a closed set. So the unvisited set is all of these basically that to start, the things you haven't been to. So let's go ahead and put that in here. Okay, there we go. So we have an unvisited set and a visited set. As we visit a node and do all the calculations for that node, we're going to move it to the visited, and we never visit it again. But we need to do one more thing. The distance from A. So we're going to make the assumption here that if we don't know, we're going to call it, it's infinity distance. We have no idea. In theory, as far as we know, since we haven't checked, it might be impossible. So we are going to assume impossibility. Except for A, the distance from A to A is obviously 0, because we're already there. That is important for the calculation. And the rest of these is considered to be infinity. Keep that in mind. I'm going to leave them blank. If this is blank here, assume infinity. Got it? Because that's what we start these out as. You start them out as like the highest possible value, because we'll need that for comparison shortly. So let's start the algorithm and I'll walk through it. Now, when we start with A, you want to compare all the edges. We can go from A to G, we can go from A to B, or we can go to A to F, and they each have their weights. If we check this one, we get the value 4. If we check this one, we get the value 7. If we check this one, we get the value 10. Now all we do here is we check and see if the value to each of these is higher or lower. Okay, so we look at G. We can see that going to G from A takes 7. So that's clearly lower than infinity, thus we fill it in. And we see that going from A to B is 4, which is also lower than infinity. So in the B node, we fill out a 4. And we can see that going from A to F is 10. We are now done with A, so we move A from the unvisited set to the visited set. But now what we do is we go to the next minimum value on this chart. So A's done. We'll do a little red here. So we look at this one, because 4 is less than 10 and 7 and all the infinity. We don't count the 0 anymore because it's visited. We're only looking at the unvisited lowest. B being 4 is the lowest. So we work with B next. So looking at B, B can also go to F right here. B can also go to G right here. And B can also go to C. So we update all those. But we do take into account this 4 value that B currently has. So if we're going, let's look at the F first. F's current value is 10. But coming from B, it is 4 plus 2, which equals 6. You see that? So now this F, oh, I'm sorry, I missed one critical thing last time. The previous vert. Now, anytime you update these numbers, you also update the vertex it just came from. Obviously, these all came from A. That was the previous vertex on those values. So anytime you update it, you also update that. So now going from B to F, we get a total of 6. 6 is lower than 10. So we fill that out and update the lowest vert. So this is now going to be a 6, and this is now going to be a B. This is 6, and it came from B last. And we can go to G and check out G. So 4, 5, 6, 7. 7 is the same. So this actually brings up a case where you kind of have to choose. Okay, so if they are the same, it doesn't matter. In that case, we are going to leave it. We are not going to update G. We're going to leave it the same. And then we also want to look at from B to C. B to C, well, C is currently infinity. So we're going to calculate it up with a 4 plus an 8. And it looks like we get 12 in this case. So to get to C, it's going to take 12. And we came from B. And we are done with this iteration. We've updated what we can update. And everything's good. And we're done visiting B. B can be added to the list of visited nodes. So now we want to go to the next lowest. So it looks like out of 12, 6, 7, and a couple infinities, that 6 is the lowest. So we're going to go to the 6. Now 6 is an F node. F node doesn't go anywhere. It's kind of in a corner. So there's actually no work to do. We've already visited B and A, and we already have those values. We moved it to the visited. Let's check the next one. We've only got C and G, and they're 12 and a 7. Well, the 7's obviously lower, so we're going to go to G. And from G, we can see that we can get to D, and we can see that we can get to C. Now, going from G to D takes whatever the current value of G is, which is 7, plus 6. So we get 13 to get to D. Hey, that's lower than infinity, so we got something to work with here. So we put a 13 here, and we say the last node visited was G. And we can see that going from G to C, oh, I didn't give this one a value, random number 7. So we can see from going from G to C is the current value of G, which is 7, and then plus another 7. So it's going to be 14. And it looks like that's not the shortest path. It's because 14 is not lower than 12. Thus, we're not going to update it. We already have a shorter path, so we don't even want to know it. We're just going to get that one out of here with this minification. But at this point, we have checked both those nodes. We're done with G, and we can just update accordingly or move it to the visited set. And then there we go. We see C, D, and E left. So if you're doing this in code, obviously you need these variables, and you're going to need some pair comparisons. But second episode, be sure to subscribe if you don't want to miss the coding up of this in an example. All right, let's visit the next lowest. We've got C and D. So the 12 is the lowest, and that's at C. All right, so we want to check all of C's paths. Now C can go to D, or C can go to E. And we take C's value, 12, and add 1 to go to this D. And we can see that we get another 13. 13's the same, so it doesn't matter what we do. We could take it, we cannot take it, we just have to pick one. In my case, in my particular algorithm, I'm going to say if they're the same, we're going to leave it. But you could just as well say to take it all the time if it's better. It doesn't really matter in this case. This is a greedy algorithm. So you're making optimal choices every iteration. You're not looking at the end goal ahead of time. That would be more of a depth first search, which is less efficient, but might give you a better end result. So since this is a greedy algorithm, it's not necessarily going to get you the best end result. It's going to get you the best result locally per node. And when you add them all together, you very often get a very good result for very cheap. So that's the point of it. That's why it's used in pathfinding, because it's very cheap. You could do a depth first every time with your game, but oh boy, is it going to chug when things are pathfinding. They'll pathfind well, but it's going to chug. It's going to have a hard time getting there. All right, let's go ahead and do this. So we're not going to update that. We're going to leave that one the same. All right, let's look from C to E. Now E is infinity, so we can update. We're going to add C's 12 plus this new 5, and that'll turn into 17. And we last came from C. And now we can mark off C because we're done with it. And now the next lowest is D. So from D, we only have one path, and it is. So boom, to E. So we take D's current value, 13, and add the 4, and we get 17. So we see we got a little conflict of a path, but we're going to leave it because that's what we're doing in our case. And there we go. We've now visited D. Okay, the very last one we have is our end goal, and that is E. Now, obviously, we already know all these paths. There's no new paths, just like it was with F, but we do still visit these even just because, hey, they're still in this unvisited set. It has now been visited. You can just mark it, and we have what I would call our result. So now we have our path. It's done. So we've completed this run. If we passed, say if we made a function and we passed it this graph and said we want to go from here to here, this is what it would generate. And you're done for that iteration. Final path. We want to know which nodes to visit because obviously we got to move our guy, right? So when you start moving your guy, this is how you do it. We basically want to pile this on from the end. So if we look at E, well, that one's clearly the end. Then we need to know what node is before that. But luckily, we just have that right. And you can see that the previous vert is C. Right before it, we put a C. You can go to C and see that the previous vert is B. So you put a B before that. So we go to B and we can see that B comes from A. So you can see now we're back at the start. This is our final path. This is the best path. Everything else is eliminated. So at this point, we could draw it out, but essentially you would move your guy along this path. Now every frame, this is the thing, every frame, or after every move, if things have changed, like if your end goal has changed, maybe you're trying to track some other object, and your object moved to D, for example, you would have to run it again. So if it's tracking a moving object, like, you know, enemy, ally versus enemy type thing in a game, you have to do this every time. But if it's for a map that's a static map that's not going to change, or your end goal is not going to change, then you can just run through the whole thing. Hope that makes sense, but that's just to make it super obvious. So let's go from A to B, then from B to C, and then we go from C to E. And just like that, we have completed the shortest path. See if you can code this up. There are some good examples online. There are a ton of examples. This is a very famous algorithm. There's a million other videos, but hopefully this explanation is thorough enough for it to like really click and stick in your head. That's the true goal of this. And hopefully I've accomplished that goal. If I even came close, consider hitting that like button and stay tuned. Now I just want to say thank you for watching and for helping support my channel. Just watching means a lot. If you want to go the extra mile, you can, well, there's plenty of buttons. They're all over the place. You can join, you can give thanks. A thumbs up is awesome. That's the main thing I'm always looking for because it helps with the algorithm and all that stuff. But if you're willing to spare a couple bucks to help me keep making these sort of tutorials and, you know, code tech tutorial type stuff, consider supporting on Patreon. For as little as $3 a month, you can keep my livelihood improving while I'm doing this. And I thank you immensely. All right, we'll see you in the next one. Peace out, guys. I have an error here, don't I? No, I don't. Never mind. I was 3 and 7 is 10. So I was looking at this and thinking, is this cheaper? But obviously it's not because it's 10 total if we go to G. Anyway, little side point that my brain just decided was a good idea to bring up.